Good afternoon, class. Here is Chih-Heng Lu, the organizer of this online SAR course. I would like to introduce you the speaker today, the Professor Kuo-Hsin Tseng. You can call him Stephen, right? Stephen. Yeah. So Stephen now currently is a served as the associate professor in Space and Remote Sensing Research Center, National Central University, Taiwan. He received a PhD degree in Department of Earth Science, Ohio State University, United States. And his research interests include satellite geodesy, SAR data processing, and multispectrum analysis. And today, the topic he would like to deliver is surface deformation and sea level rise. Okay, Stephen, the stage is yours.
Okay, thank you, Professor Lin, and good afternoon, everyone. So I'm Stephen. I work on altimetry, the radar altimetry, and also InSAR, synthetic aperture radar, and also optical data for a couple of years. So today I'm gonna share some of the experience and some research outcomes with all the students or all the audience here. So as you can see from my topic, today I'm gonna talk about sea level first. So how to use the so-called altimetry data to monitor the sea level rise, how to measure the sea surface height from radar altimetry. And because at the coastal area, the surface deformation, especially the land subsidence, is a severe issue for many of our countries. So the surface deformation monitored by interferometry, SAR, the synthetic aperture radar interferometry, is also a key technology that to see the vertical motion of the land. So in the end, we try to talk about the relative sea level rise. So when we use this keyword, relative sea level rise means that the rising of the sea surface is actually slower than the subsiding rate of the land. So actually, when we talk about the coastal hazard, we talk about how the protection of our coastline, the land side, the landward motion is stronger than the sea surface rise itself. So basically, we need to integrate both data set and to have a synoptic view of the issue around the coastline. So I'm in National Central University, and my main affiliation is CSRSR, and I also with Institute of Hydrological and Oceanic Science, and also Department of Civil Engineering. So this is the first slide. It's basically a background discussion about our current sea level trend. To the left, I don't know if you can see, probably you cannot see my cursor. So let me see if I can have my cursor on pointer. I don't know, can you see? No, you cannot see my cursor or pointer. Let me see. Screen. Okay, it's all right. So the left panel, the left figure is the sea level rise, the sea level record dated back to some 140 years ago, since 1880s. So you can see earlier this, since there is a tide gauge, then they try to track the sea level change. So basically, to maintain the tide gauge is quite difficult. Sea level that you need to record the sea level every 6 minutes, or at least you need a daily or even hourly readings to ensure that you can have a good tidal variations that already in your record. So basically, to maintain a tide gauge is quite difficult and quite you need to put a lot of effort on the maintenance. So you can see that since some more than 100 years ago, there is a tide gauge somewhere in the world. But however, it's just a point reading. So for one station, the tide readings or tide records cannot like a representative for the entire world or the global oceans. But as you can see that for certain stations that tell us the story about sea level rise. So in that probably 100 years from 1880 to all the way to 1980s, in this 100 years, you can see the sea level trend is about 8 centimeters. So 8 centimeters in this 100 years. So basically for 1 year, it's about less than 1 millimeter. So basically it's a very small rate of change. But you can see that to the right-hand side, this is in the satellite altimetry era, that since the TOPEX. Earlier, actually, there are other altimetry satellite called ERS or even earlier, CSAT. But the SETI record can be dated back to some 1990s. So since then, you can see the current sea level trend actually is much accelerated than some 100 years ago. So you can see the current sea level rise trends is about more than 3 millimeter per year. So you can see a sequence or a family of altimetry satellite like a TOPEX and the JSON, and following that we have JSON2, and now actually a lot of altimetry satellite currently flying in the orbit like Cryosat2, like Sentinel-3, Sentinel-6, and so many altimetry satellites that try to have a better coverage of the global oceans to make sure that we can understand the rising rate at different locations around the world. So basically, you can see in the last some 20, 30 years, the rising rates had a slightly accelerated. But if we check more recently in the last 10 years, we can actually find a more accelerated rising rate from this kind of data. So this is try to tell us and give us an idea. At least we know the scale. The rising rate of the sea level is about some millimeter, 3 to 4 millimeter per year. Actually, compared to the land subsidence rate, is a very small one, because for some of you who have already worked on InSAR or land subsidence issues, that in many alluvial floodplain, like in these mega cities, probably in Indonesia, in Taiwan, and in mainland China, many mega cities, very populated land. Actually, the overpumping of groundwater gonna induce several centimeter per year rate of the land subsidence. So it's almost 10 times stronger than the rising rate of sea level. So actually, how to mitigate or how to reduce the rate of land subsidence, to me, is more important or more urgent than how to stop the sea level rise. But anyhow, sea level rise is actually a very complicated issue, because it's an integrated problem that comes from the melting ice and also the thermal expansion of the water and some thermal haline circulation issues. So it's a very complicated issue. It's also a global issue. But the land subsidence is also a global issue, especially that period it happened at some heavily populated cities. So I think it's a very hot topic for many of us to understand more from satellite data. So I think it's already several weeks till now. So here are some keywords. I try to refresh your memories, because when we talk about the satellite data or a mission, here are some keywords or key elements that we need to understand first. For example, I hope that everybody had already know some basic backgrounds of orbital dynamics and elements, and also understand what the meaning of payload is. We have a main payload, we have operational payload, we have experimental payload, and we have some supplemental payload like a solar panel and other, except for the bus, except for this, the core of the satellite itself. There are some other instrumentations that are mounted on board the satellite. So each payload has its functionalities that help us to achieve some of the measurement or try to maintain the operation of the satellite itself. And some other keywords in remote sensing technologies, we have different mode of sensors. I think in this series of talks, we talk about SAR or radar, which is kind of active one that can emit electromagnetic wave from the power recharged from the solar panel. So we can send out microwave data, which is not given by the sunlight, because sunlight gives us a spectrum from ultraviolet to about shortwave infrared. So that's the main spectrum from sunlight. But for the longer wavelength that we want to have an artificial signal, so we design such a passive sensor that can see the interactions between the ground object with this kind of specific wavelength. So it's in the atmospheric window. The signal itself can go through the atmosphere, not only the ionosphere, but also the troposphere without significant attenuation. So here the keywords or I want to emphasize, radar itself is weather-free. It's basically sunlight or solar-free, that we can work day and night. So that's the basic introduction about radar satellite. But however, don't forget that this particular wavelength, when it go into the atmosphere, it actually affected both by atmosphere, the troposphere, and ionosphere, even though it can travel without significant attenuation. But as you know, the signal, when it go through the ionosphere, it can will cause the so-called group delay or the phase advance. So when we measure the distance, then we need to consider this media effect. Same as the troposphere, the low atmosphere level. This troposphere, different dry and wet pressure will also cause different kind of refraction of the signal. So it will also cause some excessive path length of the signal. So it can work under different kind of weather conditions, but for certain circumstances or for certain environmental conditions that we need to have to apply appropriate corrections for that media effect. So don't forget this some very technical and also details knowledge when you work on SAR data or in general radar data. So I believe you understand the band. We have single band multispectral hyperspectral. That's mostly for optical data. In SAR images or in radar domain, we normally just have multispectral because we have different kind of polarization, and we have at least 2 layers. One is a so-called intensity or amplitude, and one is called phase. So we have different layers. Then we can call that a multispectral because we have different kind of response of the scattering response from different energy sources. And it's quite important to understand your target because once you know what you are trying to measure, then pick up good tools and appropriate signal obtain or to achieve your goal. So, for example, if you want to understand the detailed movement of very subtle movement of the length subsidence, probably you need a C-band or X-band data. If you want to understand for a thin layer of canopies, and you want to understand what the slope movement or the creeping fault, what is the whether there is a movement, a displacement or not, probably you will choose L-band, which has a longer wavelength and with a better chance to see the rock, the moving of the rock instead of this canopy noise. So basically, pick the right satellite, the right wavelength, and the right repeating cycles for your study. Some other keywords, for example, QA and QC. So every time when you get the data, don't forget to validate and verify that. So there are two kinds of jargon or terminology. One is called CalVal, the calibration and validation. And for some agencies, they prefer to use VMV, the verification and the validation. So they are mainly the same thing. So it's try to remind us when you grab some data from a data portal, don't forget to first check whether it's the correct data you want to use, check what is the unit of that, what is the limitation of that, whether there are some extreme values, any probable or known issues or known blunders, outliers that could exist in the data set. So that's first you need to know and try to filter it out. And the second is try to validate all the data set by yourself. If you can find some external data source with better quality, if you can measure some in situ data by yourself, you can bring a hyperspectral equipment to the field and to check whether the satellite measurement is correct or not. So in any case, that you need to understand well of the data set you're currently handling, and then know what is the limitation is quite important, because satellite data, although it's very easy and very easy to use, or you can use some programs to measure something, but anyhow, the quality itself need to be controlled first. And some applications. We have a lot of applications that that will be depends on your field of study, and this is very important because know your target before choose the correct tools or correct procedures to achieve your goal. Okay, so these are the background. This is a spectrum, so probably you have seen this in the first few weeks, but now I just try to remind you once again. In the radar domain, there are actually a lot of different wavelengths. We assign a specific name for that. So for example, in the visible light spectrum, we have from purple or from the violet to the red. So that's the visible band. So we just assign some names for that, like green, blue, and yellow. And for longer ones, we have infrared and other names for that. And in radar domain, we also assign a name for it. So for example, the shortest band that commonly used in the satellite, onboard satellite is K-band. That's the altimetry data. And for the longer one, commonly seen radar SAR satellite is X and C, X band and C band. So they are at the wavelength about 3 centimeter to 5 centimeter. And the even longer one, GPS is also use a radar signal. So it's L band. It's the wavelength is 20 centimeter. And like other some radar SAR satellite, like ALOS 2, they also use L band. And later on, some, I don't know, 1 or 2 years later, we have InSAR. So it's a mission between India and NASA. They were gonna use even longer wavelength. So it's just a name of that, but keep an eye on the wavelength, the scale of that in few centimeters. So why choose this? Because remote sensing, the core principle of remote sensing is to see the scattering behavior between the wavelength of the signal and your particle size. So that the basic fundamental principle of remote sensing. So when you have a target, that's which is your particle or your object, you try to measure that, then you will select some wavelength that's longer than its particles. So basically, you can see the interactions when the signal hits the target. Then you can basically measure the backscatter behavior, the backscattering coefficient, or the so-called radar cross section. Then you can understand what is the structure, and also what is the size, and what is the density of the object. So it's basically when you have identified object, then select your appropriate wavelength for your target. So here is today's session. That's try to have an overview of something like orbital elements first, and also the altimetry, how to use radar to measure the sea level. And I'm gonna give you a very brief introduction about GRACE. So it's basically a mission that to monitor the global ocean mass change. And then I'm gonna show some results of InSAR and the land deformation that in Taiwan. And we can combine this together that we can discuss the so-called relative sea level rise issue. Okay, so this is orbit characteristic. I just want to quickly go over it. I don't know if you have seen this figure or this kind of symbol before. Normally, when we try to present where the satellite is, or to present what the functionality of the satellite, that we can, when you see these Keplerian elements, then we have a rough idea how this satellite gonna work, or what is the purpose of this mission. So the first is semi-major axis. So semi-major axis is it means how high the satellite would fly. So it's basically the size of this orbital plane. And the second is eccentricity. The eccentricity means how flat this orbit is. So basically, for Earth observation missions, the eccentricity is about 0, because we want to have a very steady angular velocity of the satellite, and we want to have a very constant distance between the satellite altitude and the surface. Because the eccentricity gonna change the distance from the satellite to the surface. So a near circular orbit is what we commonly define for the EOS, Earth Observation Satellite. And the third one is right ascension of the ascending node, basically describe what is the orbital plane orientation in the universe. So if it's a sun-synchronous orbit, this right ascension of the ascending node gonna change about 1 degree per day. So it's basically describe the relative orientation of this plane in this solar system also. And the orbital inclination is an important element that to describe how high the latitude the satellite gonna reach. So it's like a red arrow, a red curved arrow that to the right of this slide. So basically, it's can tell whether this satellite is just revolving around the equator, or it can pass through the polar area. So for example, the most Earth observation satellite, because we want to have global coverage, so we will design an orbital inclination somewhere around 90 degrees, and if it's sun-synchronous, then it's about 98 degrees or so. So if it's just for this equator observation, like there is a Train mission for global weather and climate, then the main purpose of Train mission is to monitor the equator cyclones, so the inclination is very low. So this orbital inclination defines what is the coverage of the spatial coverage of the satellite. And the argument of perigee and the true anomaly mainly discuss where the satellite current is that compared to the ascending node or to the equator. So basically, if you are interested in orbital mechanics and want to understand more about the orbital data, the ephemeris, then you can take other courses that like introduce those elements. So when you learn this, basically when you see some characteristic of orbital elements, then you can immediately know what the purpose of this satellite is. So for example, when you see some 800 or 1,000 kilometer high orbit, then you can immediately know it's for Earth observation, and it's probably for optical or SAR data. If you see it's 20,000 kilometer high, you immediately know it's a global positioning system or so. So this is background knowledge about how we describe the satellite motion. So let's go into the altimetry satellite. Altimetry satellite is one kind of Earth observation satellite. The flying altitude is normally in the tier of low Earth orbiter. And the revisit cycle is normally from 12 days to a month to about 35 days. So depends on how dense it want to cover, and it depends on how frequent it want to revisit. So you can see the nominal first altimetry mission is the Skylab, which is in 1973. So it's already 50 years ago. There is a Skylab mission. And this Skylab mission has a very coarse resolution. So it's basically just a proof of concept. So the accuracy is just 900 meters. So basically, it's just a proof of that we can use a radar signal to estimate the distance between satellite and the bouncing target or the surface. So it's already some 50 years ago. And after that, there are some successful missions like ERS-1, Topex Poseidon, and the EnviSat. They are all very famous missions that with a very long time series of global ocean observation. And since 2002, there's a new spaceborne LiDAR called InSAR. It's used green and infrared visible light to measure the surface height. There are some good and bad things, the pros and cons. Advantage is that we can measure the surface at a very small footprint, because before, when we use the so-called pulse-limited radar, the footprint is very large. It's some kilometers of the footprint. But for InSAR, because it's light and the beam width is very small, so actually the footprint is very small, just a few tens up to a few hundreds of meters. So it can measure some details of the surface height. So earlier we have InSAR, and now we have InSAR-2. It's a follow-on mission that also use green beam lasers that to check the surface height of sea level, and also others, for example, the ice sheet, and also glacier and the mountain and other DSMs. It actually can serve over terrestrial area and also ocean area. So it's a very good tool, very powerful. But for ocean surface, because as I said, the LiDAR or InSAR and InSAR-2, it has very small footprint. So basically, once there are waves or some certain spectrum of wavelength of the waves, basically it's difficult to get the so-called mean sea surface or average surface, because there are waves, and then you cannot ensure that the LiDAR data hit at the middle of that. So we still use a lot of this pulse-limited radar. This radar have a wide coverage, so basically it can smooth out all the waves in the middle. So there are a lot of altimetry mission currently working. So like Crustal 2 and the SAR Altica is probably already terminated. Sentinel-3, Jason-3, and the Sentinel-6. Sentinel-6 is similar to ENVISAT. It's a microfluidic mission, which has a function of altimetry and also remote sensing, the major ocean color in the meantime. And also the microwave radiometer can measure the atmosphere at the meantime. So to serve as a correctional parameters. So basically, this is a timeline of the altimeter family. So you can see since some 50 years ago, there is almost no gaps between missions. So because when we want to decompose the periodical signal in the sea level time series, we need a very continuous and no gaps in between. Then we can understand whether it's due to different tidal constituents. Because to understand sea level, it contains different tides. So tidal have different frequencies. For example, diurnal tide or every 14 days, every monthly, there are different periodical terms in the tide. So that's why we need a very long and a continuous time series. So this is basically a schematic to show how we monitor the sea surface. So in the middle, this is called the conventional altimetry. So in the middle upper panel. So the conventional altimetry is to send out a radar signal when it hit the sea surface, and then the radar return. So you can see below that panel, there are different circular patterns. So it means that the signal interact with the sea surface, and the interaction area it expand as time being. So basically, we can measure the strength of the return signal and understand how high the surface is, or what is the time latency between the emission and the reception of the signal. So it's a very conventional pulse-limited radar, how it works. Currently, we have a so-called delay Doppler. It's a so-called SAR altimetry. The function is similar to SAR because SAR utilizes delay Doppler. So the Doppler has a frequency shift. When the satellite receives the signal, the frontward signal will have increased the frequency, and the signal bouncing backward to your along track side, it will have a decreased rate of frequency. So we can further decompose this return signal from different orientations by analyzing their frequency shift. So it's called the delay Doppler altimetry or SAR altimetry. So basically, over ocean area, the current very trendy observation technology also use the Doppler shift idea. So basically, you can see the lower right panel with this green bars in the middle. So basically, when we apply this delay Doppler analysis, that we can reduce the footprint size, because we can divide the circular footprint into different stripes from forward to the backwards. So in this figure, the stripes is up and down side. So every 300 meters, we can analyze what is the sea level at that certain particular stripe. So it can increase the resolution when the satellite moves toward the coastline, or when it moves toward very small islands. So conventionally or before that, we cannot really analyze the ocean surface when there is we call that contamination or other signals bounce from the land. Then we cannot really calculate the sea surface height. But now, applying this SAR altimetry technique, that we can have a better understanding of coastal sea level. So to the right, it's the idea of ISAT-2. So ISAT-2 is it's a LiDAR, spaceborne LiDAR. It's send out 6 laser beams simultaneously. So it has, on the ground, it has 6 tracks because it can measure 6 places at the same time by having this kind of design. And they also have a design of 3 strong and 3 weak beams because different strength of the beams have its unique penetration capability. So it can measure whether it's from the top of the canopy, the bottom of the canopy, from the surface of the water, or from the bottom, because the green laser can penetrate through water. So we can also analyze the depth of the water if the green beam laser go into the water and can bounce back in some visible depth. So for example, 30 meters, we can measure the depth of water. So basically the principle of altimetry is to measure the travel time. It's a 2-way travel time. So when the satellites send out the signal and when you receive the backscatter one, it's basically a two-way travel. It's a round trip. So you divide it by 2 and times the speed of light, then we can get the distance. Then we know how far away the target is, and by using some data, we can understand how high the surface is. Once again, there are a lot of missions, either from European Space Agency, from NASA, or from other countries. So an example of ENVSAT has a radar altimeter payload called radar altimeter 2. It's send out Ku band and C band signal all together. If you have learned GPS before, then you know the dual frequency is very effective to cancel out or to mitigate unsphere effect. So for radar altimetry, they have a very similar design because 2-band can understand the effect of unsphere delay. So once we remove that, we can have a better range estimate. So there are some other payloads. So for example, MARIS is for ocean color, and NWR is a microwave radiometer. That's used to estimate what is the water vapor pressure of the troposphere. It's also important correctional terms for radar altimetry in the distance. And ENVSAT has InSAR. So if you played around some old InSAR data, InSAR is on board ENVSAT, and some other payloads. This is some computational procedure to obtain the sea level height. So before I said it's quite straightforward because when we have a time delay divided by 2 times the speed of light, that's basically the range. As you can see to the upper left, there's an equation, there's a range. So once we have the orbital height and subtract the range and plus some corrections, we can recover the surface height in certain data. So the correctional terms include the tropospheric terms and ionospheric terms and some others, pretty much similar to synthetic aperture radar, because when we use radar to measure distance between 2 points, then we need to know some media effect, and also some tidal effect. So for example, it's similar to InSAR displacement. When we have a time series of surface motion, that you say that I use small baseline subset or I use persistence scatter InSAR, we have a time series of land motion. Actually, don't forget, this signal involved a lot of periodical terms that naturally exist on the surface or in the target. So for example, when you measure the surface, there is a so-called solid earth tide. Solid earth tide is like the ocean tide, but is occurred over terrestrial area. So all the land actually gonna move out and move up and down actually daily because of this lunisolar attraction. It's just like ocean tide. Ocean tide has a tidal variation with the amplitude of some 2 meters or more than 2 meters. The solid earth tide is our land, our solid earth actually gonna move up and down, also because of the sun and the moon's attraction force, and the amplitude is some 20 centimeters. So when you measure some up and down, that we can actually see this from the GPS time series. So we need to take it out. If you have a known, already know the periodical, the amplitude of solid earth tide, try to remove that in your time series, because it's not real. It's not the artificial or some tectonics or some fault activities. It's just some nature behavior of the land. And we have also other tidal terms, so like ocean tides. And there is actually another called ocean low tide, is that when we are measuring some coastal area, the sea surface change will have different ocean load. The water have its mass loading. And this mass loading gonna press the land also up and down at some 1 to 2 centimeter level. So those are the periodical terms we need to consider, either in altimetry data and for InSAR data. For ocean observation, we need to consider more like a sea state bias and inverted parameters. So different air pressures gonna cause surface topography change, and so on. And one key processing of altimeter data is called waveform retracking. So the retracking is to analyze the backscatter signal and to define where is the most likely height of the surface, what is the most likely delay of the time of the signal. So it's a technique called waveform retracking. So again, this is a schematic, show the bounce of the signal and how we measure the sea surface. So you can see from left to right, the power received as a function of time. As you can see, when the signal hit the ocean surface, the expansion of red area, it means the stronger signal gonna bounce back. So you can see the return signal will increase in time. And as time being, when the circular expansion of the interaction zone, the glistening zone, becomes a donut shape, becomes a ring, which means the interaction area is smaller because the ring area is smaller than the solid field circle. So basically you can see the power start to decrease. So basically we use what is the strongest power, what is the most representative time, is the time we say where the surface is, the mean sea surface is. So this is below this shape is called a waveform, and to track or to retract that is a technique called retracking. From this waveform, we can understand some ocean pattern. So for example, the skewness and the trailing edge slope, there are several parameters. When we analyze this waveform, we can understand if the surface is very rough. The roughness means that when the signal hit the surface, hit all the waves, then the scatterness is very strong. If the scattering is very strong, which means the received power gonna be increased gradually not a very sharp return. So if the skewness is, if the leading edge slope is not so steep, if it's steep, it means the ocean is very calm. If it's a little more gradual, which means the ocean state is very rough, which means the wind speed is very strong. So basically, not only to analyze the sea surface height, but from this waveform, we can understand what is the sea state, what is the significant wave height, and we can use an empirical function to derive how strong the surface wind is. And this is an actual waveform that we are dealing most of the time. It's actually not so ideal because the scattering process is very complicated when the signal hit the ocean surface. So this is the first product that probably you have seen this animation before. It's from NASA. We can see some eddies and the current and the different ocean patterns. So for example, when you see this red spot to the east of Pacific Ocean, so that's the signal of El Nino. So if we have a reverse sign, we have not so red or not so expanded sea surface, and we call that La Nina. So probably you know this global climate pattern. We have a periodical pattern. So you can see that some eddies, not only this huge pattern, a huge pattern appears near the equator of the Pacific Ocean. We can detect whether there's a El Nino or La Nina. We can also see some small currents and eddies. For example, to the east of Japan. So that's the crucial current when it's moved from east of Taiwan all the way up to the North Pacific Ocean. There are small eddies that to the east of Japan. Then we can see whether these eddies has some anomalies that are different from earlier years. So we can analyze whether the ocean pattern has some anomalous change in this year. So it's so-called the instantaneous sea surface height. And for a global pattern, I think everybody is quite familiar with the so-called geoid, because when we want to understand the shape, the gravity field of the Earth, we need to know where the mean sea surface is. So it's a good approximation of the geoid, or vice versa. So basically, we need to know where the mean sea surface is. It requires a very long, continuous observation. So you can see our geoid has the highest part is to the east of Indonesia, and the lowest part is to the south tip of India. So basically, how we know that? Because we have a repeating observation from altimetry data. After removing all these periodical terms, all the tidal terms, then we can have a very static presentation of the sea surface that is extremely calm without this periodical amplitude. Then we can derive such a product. So you can see that the global mean sea level has the highest to the lowest point is about plus minus 100 meters. So that's so-called the shape of the Earth. Okay, so this is another mission.
Sorry, Stephen.
Yes.
There is a question from audience.
Okay, okay, maybe I answer your question first. In altimetry, we know the aliasing problem. How long does the data take to produce the ideal sea surface, right? For example, there are the aliasing means that when you have a periodical term, and if your sampling rate is not higher than half of that, it's called the Nyquist frequency. So if you want to understand what is the amplitude of so-called daily diurnal amplitude, diurnal signal, you want to know the amplitude. Your sampling rate cannot longer than half of a day. So that's the minimum requirement of the Nyquist frequency. However, because as I said, the repeating cycle of the satellite is very long. It's either 10 days or 35 days. 10 days is for JSON series, 35 is for European MVSat and the Sentinel series. So we need to handle this aliasing problem. And it depends on what signal you want to decompose. So if we want to have to understand this S2 tide, or for example, this the signal twice per day from sun or from the moon, actually we need, for example, a couple months of observation that we can collect enough samples to solve this anti-aliasing problem. But the longer wavelength, or the longer periodical term we understand, we actually need a even longer time series. So once again, that's why we need a continuous and then no gaps between the satellite missions. Because, for example, if I remember correctly, there is one long periodical term that requires at least 1 year. What is the amplitude of that component, or so-called tidal constituent? So basically, it depends. Not say 3 months or 4 months. I can solve all the tidal components, but to my understanding, at least 1 to 2 years, no gaps in between. Then once we have a monthly sampling, then we can almost solve all the periodical terms. Hope I answered your question at this moment. Okay, so this is so let me resume. This is ISAT data. ISAT 1. Actually, the official name is ISAT. ISAT, it has 2 wavelengths. One is green, and the one is infrared. So infrared is to measure the cloud height and the canopy height. And the green beam laser has a better penetration, so it can go through the canopy and they go to very shallow water. So they have different penetration capability to have different layers of products. So basically, if you have played around with LiDAR data, you know there are several strategies to analyze the data. It depends on the equipment, whether it's a full waveform LiDAR or it's has a photon counting system. So for some LiDAR data, it doesn't really provide the full waveform, but it gives you some layers with the highest or the dense light photons return. So basically, the waveform analysis similar to radar waveform. We pick the highest or the most dense timing. When do these photons return? Then we call that's the most probable time delay. Then we can convert that into the distance. So we can analyze the so-called full waveform LiDAR waveform. LiDAR can give us different penetration to the layers. So if there's a canopy that it has a multiple return, then we can understand whether it's from the surface, the very surface of top of canopy, or from the bottom of the canopy. So we can also use that to analyze the canopy height or some thickness of some layers on the ground. There is a new ISAT 2. ISAT 2 is a new mission. As I said, it can penetrate through water. So basically, when it goes through a shallow water area, you can see this is the LiDAR return. The point cloud can tell us one layer is the ocean surface, and then another layer is the ocean bottom or the sea floor. If the water clarity allows, if the penetration is enough to go through that. As I said, some clear water, the penetration code can go as deep as some 30 to 40 meters. And further, we can analyze the point cloud and to recover the bathymetry. But ISA2 also provide the sea surface height product, because in this class we mainly focus on the sea surface rise. So here's just an example that the LiDAR data can also give us a very accurate measurement of sea surface height. So this is the ground track of LiDAR data. It basically has 6 simultaneous measurements. So the density is it's very dense. So every 70 centimeters, there is one sampling of data. And the interval between tracks is just 3 kilometers. So basically, it's provide us a very good global coverage. So it's a repeating slides. Say by using all those altimetry missions that we can construct such a seamless, continuous time series. This is our current rising rate, 3.4 to about 3.4 millimeter per year. That's from NASA's analysis. And to the right, try to give you an idea that actually the global sea level rise is not it's not the same everywhere. We have a so-called eustatic sea level rise. It means that global ocean has a mean expansion. So that on average, we call that eustatic. However, among this eustatic global expansion or a rising pattern, there are other high frequency terms. So you can also imagine global ocean sea level rise has a first order expansion. It's called eustatic sea level rise. And some higher orders, second order and third order, is there are some local effect. As you can see from the right figure here. So the red part, it means that in a certain period, some ocean has very strong rising rate. So for example, in the Midwest of near Indonesia, the sea level rise could be up to 5 to 6 millimeters per year in this particular time span, 1993 to 2016. But you can see in the meantime, some area actually the sea level is lowering. Sometimes the lowering is because there are some static current. And when the current become more and more sharpened, so the slope of the sea topography becomes steeper and steeper. So one side is rising, another side is declining. So it's like the east of North America. So you can see that a very strong contrast of sea level rise trend. So basically, it gives us the long-term sea level rise is an issue, but among them, there are some periodical terms. So for example, in this 20 years, which area has the fattest sea level rising rate? Then we need to predict how long it's gonna last. If it's going to keep the same rate or it's going to even accelerate. And for some other area, if it's relatively calm, then probably you need to put your resources or aim on some coastlines that has a stronger relative or sea level rise rate. This is an analysis based on some projections. Now we have AR6. IPCC every some years that it will release a new report showing that what is the century end, the end of century sea level rise scale. So earlier they use these scenarios like A1, F1, A2, and B1, and in the latest report they use RCP. So it means that how much we rely on these fossil fuels and how strong this greenhouse gas gonna stay in the atmosphere. So the strongest RCP 8.5 is similar to the AR5. But in AR5, it's similar to the B1 projections in earlier report. So for those series of reports, they mostly conclude that the sea level rise without very extreme storm surge or tide surge, the sea level rise rate is about 80 centimeter to 1 meter to the end of this century. So basically, it's a bottom line or a benchmark that when we try to predict what is the sea level rise rate induced coastal hazard, then 1 meter of sea level rise is some extreme assumption. There is a website called Sea Level Change offered by NASA. It's actually give us an interactive and recent rate of the sea level rise rate. For example, you can click on different places and it tells you what is the current sea level rise rate. And under some scenarios, greenhouse gas scenarios, what is the end of this century projection? So for example, near Manila, their projection is about 1.46 meters rise of sea level. So probably you can go Google it and check what kind of rate that closest to your hometown or your office. The sea level rise rate, is a global issue. So for example, this is Bangladesh. Bangladesh also encounters such an issue. In the Gulf of Bangladesh, actually sea level rise rate is calm. It's some 2 to 3 millimeter per year. But the land subsidence rate is very strong. For example, in the middle near Dhaka, the subsidence rate is more than 1.5 centimeter per year. And you can see we can have some projections. This red area and the red area are the projection of sea level rise. When the land keep going down and when the sea surface keep going up, then what is the inundation area? You can see the middle figure is 100-year projection, and to the right is a 200-year projection. So you can see if we keep the same rate of water pumping, and if the aquifer, the condensation of the aquifer or the compaction of the land keeps going on, then actually the scenario gives us a very worse, a very bad projection of coastal hazard. So sand analysis can also apply to different areas. For example, this along the China coastline, and to the right-hand side is around the Vietnam's coastline. So because Vietnam coastline, it has a stronger tectonics than the sea level rise. So because the land upper going up, the vertical motion is very strong. It's several centimeters per year. So actually, the sea level rising rate is far behind. It's much slower than the rising rate of the land. But you can see to the left along the China's coastline and other places, most of this land area is actually subsiding. So it's quite an issue. Another mission that can help us to understand is called the GRACE mission. So GRACE mission is a twin satellite, one following another. Basically, it used the very subtle perturbation of the orbit to recover what is the mass change below the satellite. So it basically operated between 2002 to 2015, 2014. So in that time, we have a monthly gravity anomaly. And so monthly we can have a solution. What is the mass change of the Earth? So basically through some spherical harmonics presentation, I'm not going into the details, but it gives us what is the periodical terms, the spatial periodical terms of the Earth's shape. So we can see the migration of the Earth mass. So for example, there was a mass in over the Greenland of the ice sheet, but next month or next year, we can see the mass loss, the decline of the mass, because when the satellite flying over the Greenland area, then the orbit acceleration is different than before. Then we can understand there must be some gravity change or mass change down below the orbital, the orbit. So here is
as the front satellite approaches an area of higher gravity,
animation.
it will be pulled toward the area of higher gravity and speed up. This increases the distance between the two satellites. As the satellites straddle the area of higher gravity, the front satellite will slow down, and the trailing satellite will speed up. As the trailing satellite passes the area of higher gravity, it will slow down, and the lead satellite will not be affected. As the twin satellites move around the Earth, onboard instrumentation measures the distance between them, which is caused by the speeding up.
So this is an idea how to use a GRACE mission. This is just for your reference that we have such a mission existed before, and now we have GRACE follow-on mission that can recover the Earth gravity field, and it can tell us a very large-scale movement of the mass. So this product can also derive an instant gravity field and a mean static gravity field. So this is some gravitational field reference. And by using this product, we can understand the gravity movement. So for example, the lower panel, the upper panel is that the gravity data itself contains some aliasing or stripes that we need to filter it out. So eventually we can derive the product like the lower panel. So you can see the lower panel is basically tell us, so for example, in the 10 years period, what is the mass change in different places around the world. So you can see the very dark patch to the upper right is a Greenland mass loss. And you can see the warm color next to it is basically the so-called post-glacial rebound or geostatic isostatic, glacial isostatic adjustment. So it's because in the late ice age, there are a huge chunk of ice that press the land downwards. And nowadays, the land will bouncing back. So we see a increasing trend of the mass. But you can also see some other decline of mass, like Alaska glaciers and Antarctica glaciers and so on. So this gives us an idea whether there are some mass earlier it exists over land, but now it's go into the ocean. So we can quantify how much water that melting out, wash out from Antarctica or Greenland. Okay, so I'll go into SAR part, the synthetic aperture radar. Everybody know it can monitor the land motion by using interferometry. So we have a prior pre-event image and the post-event image. When we make the difference of the phase, we have a so-called interferogram. And we can unwrap the interferogram from the reference point, then we can have an accumulated displacement. So this displacement can tell us which part is moving away from the satellite or which part is moving closer in the relative data. So by using this data, that we can understand some phenomenon. So for example, in the Western Taiwan, the land subsidence is a very severe issue. We have a range between 1 to more than 6 centimeters per year subsiding rate. So this is the background. It's a very hot spot that many researchers working on SAR data try to understand the mechanism and also how severe the land subsidence is. So we can use Sentinel data. Hopefully that you already had a chance to play around with these data sets. We won't have any more Sentinel 1B because it's terminated. Now we have the Sentinel 1A, and luckily in Taiwan we have both ascending and descending track, very continuous and steadily imaging over the island. Sentinel 1A is good at InSAR because of their high orbital accuracy. The orbital control can maintain the orbit in the 50-meter orbital cube. So basically, when we do the interferometry, it's very important to know the orbit location, especially the baseline needs to be close to each other. Otherwise, if the baseline is too long, then there are some restrictions when we try to detect the land displacement. So basically, if the orbit can overlap in their repeating cycles, that's the best for this kind of study. And the coverage is wide, so it's very useful for everybody. This is some background of SAR images. So the signal itself is actually a chirped signal. It's a modulated frequency. So to increase the ranging sensitivity, to increase the ranging resolution. Because when we receive the signal, if you just receive the amplitude of signal, actually the resolution is not so good. But if you can further decompose them into different frequency chips, then we can compare the signal, received signal with your replica, so we can increase the ranging resolution. And again, this radar platform, it has a long track and a cross track coordinate system. So along track we call that azimuth, and the cross track we call that range. And as I said, because the signal return relative to the right, to the to the cross track, this is called the zero Doppler. Frontward we have the increasing Doppler frequency, and the backward we have decreasing Doppler shift. So basically, we can also use this strategy to enhance the resolution along track. So combining the time delay and the Doppler frequency delay, that we can have surface imaging capability from radar signal. So this is the so-called in the illuminated area to the left and to the right, you can see there are some solid curves. The solid curve called the equal Doppler delay. So along the same solid line, the Doppler shift is the same. And you can see the circular dashed line. So that's the equidistance line, or the latency line. So basically, our range estimate, it depends on the delay of the time. So as the footprint expands, that you receive different signal from near range to the far range. So you can see, combine this together, combine the solid curve and the dashed circles, you can see it divides the lane into grids. So those grids is the imaging pixels. So definitely there are some more technical or detailed processing of the data, but you can see for a certain signal in the coverage, we have different grids. So that's why the Doppler system is an imaging system. It's not the same as altimetry data that just give us a point target response, give us a value of distance, but not a distance or the amplitude from different grid part. So the synthesis of the antenna, it utilized when the satellite flying along track. For a point scatter, it actually has been heated or has been illuminated by the signal several times. So you can see the imaging principle is like along this red dot over the orbit. For those 5 dots, they monitor the point scatter that colored in blue dot on the ground at least 5 times. So please imagine that so for a signal that when it hit the target, because of the orientation, there are constructed and the deconstructive interference. So basically, you can imagine for a point response in the image, it will appear as a sinusoidal signal. Strength will go up and down. So how to analyze 1 pixel is that along the track, when you image this point several times, say a few tens or to hundreds of times, we can analyze the strength of the response for that particular point. If it goes up and down at certain periodical terms, then we can say the target is very clear, it's very bright, so the amplitude is very strong. So if the signal along track fit that pattern. So I don't have a whiteboard, I don't have a sketch, but please imagine that it's a sinusoidal pattern that when you hit the target. And there is a match filter. If the match filter of the signal it fit the best, then we give a very high, we say it's a very bright target, and in the amplitude we assign it to a very strong signal to that target. So in this kind of process that you can imagine, we required a very long distance of satellite orbit for one target image. So this is called the synthesis of the antenna aperture. So along this track, from the first point to the last point that you see this target, we use this up to kilometer wide of orbit length. Say that's a virtual aperture diameter. So that's how this S and A synthetic aperture comes from. So similar to this target, this illustration, you can see the synthesized long antenna is that when you want to image one target, actually you image that several times. So you can enhance the resolution of that particular object. There are different strategies. One of that is the PS-InSAR. PS-InSAR is it's originally called the permanent scatterer, but because it's a trademark registered by the author. So now the open source kind of version is called the persistent scatterer. So it utilizes the steady to analyze how steady the return signal is. If it's very steady, the return signal in time is very steady, then we say it's a good object to track. If some point that sometimes it's very bright, but sometimes very dark, so for example, the canopy over forest or over agricultural zones, because those vegetations will sometimes have stronger, bigger leaf size, and sometimes it's just a bare land. So the reflecting behavior is not consistent. So we don't rely on the phase measurement over those objects. We try to just analyze something has a very rigid, solid structure that we can measure the very subtle phase change between satellite and this object. So this is called the PS-InSAR. Give you an idea, if you have an InSAR result, it's similar to this time series. From top left, that's the first state, and all the way through rows to the last one, that's the time series. So no matter which kind of strategy, even it's a small baseline subset or it's a PS InSAR, most of the time the data are going to be contaminated by some bad image, I would say. So the bad image means that sometimes there are some orbital problems, sometimes there are atmospheric corrections not being removed very well. Sometimes there are other effects like ionospheric anomaly and so on. So basically for time series, it's not so easy to explain. My suggestion is that when you have this kind of plot, don't explain the phenomenon, don't explain the time series, because you feel something weird in your time series. It's really weird. It's really contains some errors or some mistakes in your result. But sometimes just don't be so depressed, because sometimes we can try to make some corrections. So for example, in Taiwan, we made such kind of corrections because we have a very dense GPS network. So we use this GPS network to control, to make a multiple reference point system, try to control the displacement delivered by InSAR. So as you can see, here is a workflow that we grab GPS data, and after some modeling of the data filtering of the GPS data, we have a lot of control point to the middle. You can see some dotted, colored dots. Because when we are handling an interferogram, when you try to unwrap that, normally we just have one reference point. So that's a standard operation procedure, that you unwrap interferogram from one reference point. But however, if the interferogram itself contains some errors, for example, as I said, ionosphere error or orbital error or troposphere error, actually the interferogram itself is not so correct. And also, during the unwrapping procedure, there are some unwrapping errors. So for example, there are phase jumps in the middle of some features on the ground. So if you don't control it, basically away from the reference point or away from your starting point in the unwrapping stage, the longer the distance, the more errors that you will get or accumulate. So for example, if you see the upper right panel, you can see to the margin of your study area, actually it's away from your unwrapping center. So the accumulation of error will be very severe. It will be very clear. So you can see a lot of red and warm patches near north and near south hills. It's not only because the interferogram over there is not correct, but also due to the unwrapping error. So I don't know whether in your country you can grab some GPS stations that help you to make this kind of anchor point. But in Taiwan, at least, that every few tens of kilometers, we have one station. So what we have done is that we make a difference in between, and we make an interpolation by using, for example, Crustal. Then we can have a so-called correction map for the InSAR displacement. So we just subtract that air terms from our displacement, then we can have a calibrated one. So this stage we call that GPS calibration. But in Taiwan we have such a service, so we can make it done. But probably in your countries, if you don't have other GPS data, you can also use leveling. Leveling gives us at least a first order subsidence or vertical motion rate. Then you can control your InSAR data better than just rely on the data itself. So you can see what is the effect if we remove that errors that estimated by GPS. the difference between GPS and InSAR, and we remove that, we can see after calibration is the middle panel here. The time series becomes very continuous and smooth, that we can see those agricultural zones has some patterns of subsidence that becomes bluer and bluer every year. And the signal becomes very strong. And especially after this GPS calibration, it gives us a good datum, because GPS has an idea that based on WGS 84. So when we say something is going up or going down, it's relative to this data. Without calibration, actually, when you make any kind of InSAR time series, there is no data. The zero is the displacement zero. So basically, when you have warmer or cold, warm and cold color, it basically means relative motion compared to the mean, the average of this area. So basically, there is no idea about data in a traditional InSAR time series. So you need to calibrate or at least validate that with a few GPS stations. Then you can make it more reasonable or understandable, because now when you see the cold color, it really means the land is moving down or moving away from a certain reference surface. Okay, so what is the benefit we can get from this kind of calibration? You can see to the right, there's a scatter plot. The blue circles are the original scatter plot, and the green points are the calibrated one. You can see the room square error reduced from more than 2 centimeters to smaller than 1 centimeter. So that's the accuracy of the displaced measurement between each pair of SAR image. So we can further see different time series at different stations. I'm not going into details, but let me just pick up one station like KTES station that you can see there are periodical turns. So there is a secular turn and also some periodical turns in the middle. So we can use InSAR's data to understand whether this displacement is associated with some agricultural practice or other usage with such a seasonal pattern. So toward the left, this sea level rise, it has a rate of few millimeters per year. But to the right, you can see the land subsidence rate is some centimeters per year. So when we combine it together, we can make some predictions. So there are some townships that along the west of Taiwan that is more prone to be flooded. So it has a huge inundation problems in the end of this century. The darker the color means the deeper the water, or the lower the land. So basically it provides some first order alarm or caution to our water resource agencies or land administrations to understand which part is the hot spot that need to be protected with higher priority. So sea level rise is a global issue, but this is probably the last figure. I want to give you also a very interesting story. Global sea level is not always up. So for some particular area, actually the sea level is falling. So for example, you can see this Hudson Bay, so a very warm color in the Grace gravity anomaly plot. To the right, North America is the Hudson Bay, and to the left, you can probably see some orange to reddish part. That's the north of Baltic Sea. So the north of Baltic Sea, actually, because of the post-glacial rebound, the land is actually rising. So the sea level is actually going down at the rate of some 0.5 centimeter per year. So for some area, actually, they are free from the global sea level rise issue, but some part of the world is actually a severe problem. Okay, I think that's what I want to deliver today. It's probably a little bit different from the SAR lectures before, because earlier probably you learned a lot of these signals, how to technically calculate to produce the interferogram, how to unwrap that, how to explain that, what is the tectonic, what is the fault activities, etc. But today, what I want to deliver is that for the coastal area, that the InSAR data give us the land vertical motion. Then actually what we really care is the interface problem. This is called the critical zone. Critical zone is along the coastline, and the landward and the seaward some kilometers. We call that coastal zone because it's heavily populated and a lot of ecosystems. But this place is lack of observations because ocean satellite, their duty is to observe over ocean. Land SAR missions, their duty is to observe land vertical motion. But near the interface, actually how to link the data in between is a quite good topic. And we want to understand what is the relative motion of two surface and what is the consequence if the rate keeps going on, and try to emphasize that we really need such a satellite mission that to ensure we have enough data to analyze good spatial temporal coverage to analyze this question globally. Okay, I think that's it. So if you have any questions, probably you can raise your hand or you can type in the message window. Okay, now I see one question. It's your research on cumulative LOS displacement published in the journal article. It's under review. Actually, I have several reports, but we have a paper that working on ionospheric correction. So it's in advanced space research. Some 2 years ago, it's about Sentinel-1 ionosphere correction for a Meinong earthquake. But for this GPS correction, we just submitted that a couple weeks ago, and it's now under review. If it's being published, or you can, I will let you know some article you can refer to. But for this kind of corrections, there is one paper by Dr. Lu. He works on the co-correction. He used the term co-correction. He used Sentinel data and the leveling, also in the southwest floodplain in Taiwan, fluvial plain in Taiwan. So probably you can find that article to read. So it's basically also an idea to bundle the SAR data and also some ground control points together to improve the accuracy of the measurement. I don't know if any of you have questions. Probably you can just turn on your microphone and let me know, or you can raise your hand. Okay, Mr. Lin.
Okay, yeah. So good afternoon, Professor. So I have two questions. Because your slides has mentioned that the rates of the global sea level rise seems a variation in different regions. So something part of sea level rising faster, and some is slower, and other regions are negative. So I mean the sea levels is a go down. So my question is, why the sea level rise speed will different and variation at global wide. It's just because the geographic issue like the subsidence will rebound, or is it because the ocean current is distribution, the different number of the waters into the different place. So that's the first question. Oh, also another one is in some of the part of your slideshow, the negative sea level rise is not only in the land, it also happen in the ocean inside.
Yeah.
So very clearly that's not caused by the rebound. So what will be this happen? Thanks.
Okay. I believe you can still see my this shares desktop. So you can see it's not really negative. Well, the trend is negative, but why it's negative is because when this current becomes stronger and stronger, if there is a consistent current or eddies, if it becomes stronger, you can imagine one side moving up, one side is moving down, right? So you can see that along some part near this eddies or this current, because the way the current the speed is stronger and the slope, the gradient becomes stronger. So it appears like one side is moving up and one side moving down. But except for that, elsewhere actually on average the sea level is rising. Okay, so just only for this very subtle and the small patches patterns, they have a decline. But it's a very short time period. If we in lengthen this time period, then actually this pattern it could be just a periodical turn. So if we make this time series even longer, probably it will smooth out and will not see such a pattern like in these two parts. And your question also covered why some place that has stronger. It's basically also due to the thermal haline. It's also associated with the temperature of the ocean and also the salinity of the ocean, because the temperature and the salinity of the ocean is not the same. Somewhere it have a higher temperature, and somewhere it has higher salinity. So different kind of thermal haline expansion, it will have different grade or level of sea level expansion. So that's why, because the ocean is not a unified density or a unified structure. So basically, it has such a global pattern. And again, I want to emphasize some patches, there are also some periodical terms, because for this figure is from 1993 to 2016, so it's about 20 years. So it just tells us in this 28 years, this period, we have this kind of pattern. And again, if we have a longer time series, like 100 years, probably this pattern is just one of the periodical term, once again. So what we need to do is to keep an eye on this hotspot to see if it keeps increasing or it goes from this period to another periodical phase. Did I answer your question?
Yeah, so basically the sea level rise speed variations depend on the strength of the ocean current.
Yeah, and also the thermal haline, the temperature and the salinity distribution of the entire global ocean.
Okay, but because just like you say, so when the satellite, let's just use the radar and to detect the surface altitude of this sea level.
Yeah.
But my question is, in some ocean region, like in the equatorial region, near for the tropical ocean region, in this kind of ocean region, inside the storms very often at the typhoon or the cumulonimbus cloud or thundercloud. So when this kind of storm, they happen in the ocean. So though because the main is an ocean wave, and this kind of ocean wave has a very high altitude, maybe 10 meter or 50 meter, when the ocean wave merge to each other, possibly rise to 30 meter. And because for I know the radar wavelength that used to measuring the sea level altitude, this is L band or some others a long wavelength band. And when this kind of signal, when this kind of radar wave, they impact into the ocean wave and back, into the satellite in the average calculating side. So rich ocean wave region, is that possible? Possibly calculating become a high sea levels area? So that's the second question. Thank you.
Okay. The first answer is that the pole in diameter. So basically, it's a huge footprint, 5 kilometers. So for a calm and a regular or a very common calm wind, it can smooth out all these waves. So basically, when we after applying the waveform retracking, we can get the mean sea surface, and we can also get the indicator called the significant wave height. Because as I said, radar waveform can analyze the sea surface roughness. So by using the sea surface roughness, we can derive what is the significant wave height. So for some very stormy and a very windy or a very strong super high waves, let's say, of course, because the return of the signal gonna be shorter because the time elapsed, because the wave is high, the time elapsed is shorter, so the satellite will automatically recognize as a very high surface. It's inevitably because radar signal really bounce back faster than before. So in the time series analysis, quite important to detect such an anomaly, because it's an event-based observation. It will not allowed or included in the calculation of sea level rising rate. So you can imagine that the sea level time series would be a periodical terms with some extreme values. So that extreme value is what you call the event-based, some cyclones or some typhoon-induced high waves. But to calculate the secular rate, that we need to remove all those outliers, and we need to fit the periodical terms, say this is due to the lunisolar attraction. So after remove all these sharp outliers and also the periodical terms, the remaining part is we call that the sea level rise rate. So it's basically a very steady and a very long term without some external disturbances.
Okay, so my final question is, you mentioned that the principle of the GRACE mission is that the distance from satellite to satellite, it will change as the satellite flies over an area of different mass. So my question is this kind of distance change, and there will be counting variance when the distance between satellite and the land are changed? Like, for example, in a low Earth orbit and a high Earth orbit, so is this kind of distance will be changed? So this is a final question. Thank you.
Yeah, of course, because the satellite, the gravity field, it have different equipotential surface. So of course, that different level of satellite, the acceleration due to a point mass underneath the satellite will change. But the design of this satellite is that those two satellites really close to each other. It's just 200 kilometers apart. So basically, when they are flying up and down, they will go together. So they measure the distance change at different equipotential surface, and we can eventually reduce this gravity anomaly to the surface because they are really close to each other. So we basically can assume that the mass-induced gravity anomaly is the same to both of them.
So you mean want to get as possible as high as the accuracy of the mass the satellite should fly on the low Earth orbit, but not a high Earth orbit?
Yeah. Of course, because the flying altitude is 500. So that's why the lifespan of GRACE is actually already longer than its design life. The original design life, I believe, just 2 or 3 years, because it's fly very low. It's just 5 kilometers. Normally, to maintain a good satellite, the flying height, the higher the better, because it can avoid some air drag and solar radiations. Because the higher, the easier to maintain the orbit. It needs to be flying very low, because the lower, the gravity has an inverse proportional to the square of the distance. So the lower the orbit, more sensitive to the gravity change on the ground.
But low Earth orbit, it will have some gap that we have something that very thin atmosphere in here. So the air it possibly will dampen for the satellite.
Yeah,
so,
yeah, air drag.
So will it also affect for the accuracy?
Yeah, yeah, of course. But once again, they use the air drag model, try to remove that effect. And once again, it relies on the very close feature of those two satellites. So once it encounters some air drag, we assume that the air drag applied the same force to both satellites.
But air drag model, that is a standard. And we know when the ionosphere, their electron densities is changed, like when the solar storm come or some other region, the density of the atmosphere also be changed. And air drag model, they cannot filter all of this. So it's not mean the error of these satellites, they will become higher when the solar storm are coming or when the ionosphere are getting interference.
Well, yeah, definitely, because the solar radiation, if it's modelable, then we can remove that. But if there are some really strong anomalies that, for example, some ionospheric, I don't know, bubbles or whatever that only hit one of them, and of course it will immediately affect the distance measurement in between. Well, I'm not really the processor of that data, but I assume that once they detect such an anomaly, they will also remove such a readings because they have a reasonable range of distance change. If the mass if we assume the mass change is gradual and smooth, it's not a sudden change from last month to this month. It's the mass change is slow, then the distance change should be in some reasonable threshold, not like a super huge change of the distance.
Okay, thank you, Professor.
Okay, thank you very much.
There's Stephen questions.
Okay. I conduct the same research as you in the area of Jakarta. And some other places in Indonesia, I use only inundation modeling from land subsidence and the sea level rise. Do you do hydrodynamic modeling in your research like Mike 21? Okay, it's too complicated to me. I know there are some hydrodynamic model that can help us to model how this current and sedimentations, erosions will occurred along the coastline, but it's just really too complicated to me. I didn't. So the short answer is that I didn't. But let you know that one thing that I have done is quite important is that I use optical data to reconstruct the intertidal zone DEM. So that's a critical step in this study, at least to me, because as you know, the land digital elevation model, it has some limitations over land area, and the ocean bathymetry, actually the resolution is very coarse. And for most elevation model, there is a gap in between. It's called the intertidal zone elevation model. And actually over Taiwan, I built up myself by using optical satellite. Maybe you can check some maybe I can give you a reference how I did that. So basically, I made a seamless elevation model first, connecting between land, ocean to shallow water. And because you need a very seamless elevation model, then you can simulate what is the sea level rise affected land. Otherwise, for a conventional elevation model, there is a gap. So sea level is here and the land is some meters high. So under some simulations, you project the sea level goes 1 meter, 2 meter higher, but you will not see any effect to the land because basically the land is some 2 meters, 3 meters higher than your ocean surface. So you need to feel the elevation model gap first, then you can see the gradual sea surface height rise, sea level rise, then you can see the inundation area gonna expand more and more. So basically that's what I did. But I don't really use hydrodynamic model to see somebody used that to try to analyze the erosion and the sedimentation, the sources and the consequence, why there is such a sediment transportations and so on. But it's out of my scope, so I didn't do that. Any other questions? I don't know if someone raise your hand right now.
Questions from audience? Okay, thank you, Stephen, for today's strategic talk. I think you still can reach Stephen by using email.
Yeah,
right?
yes, please.
Okay, and so we almost run out of time, and I will close today's lecture and also today's the talk. So I think we also have had two simple quiz by the end of the lecture today.
Yes.
孟哲
Okay.
OK， 郑老师，谢谢
Okay, thank you. So can I log out now?
OK.
Okay. Okay. So you guys just contact me if you want. Okay.
Thank you, Professor Tseng.
Thank you. And by the way, one thing to announce from the organizer. Now we have the two invited speakers, and there will be the end of this online course. And the last week, there will be the end of November, the end of this month. We would like to invite you to deliver some of the presentations. The presentation about your study about the SAR, or it's simply a best concept, best idea. It's not a study, but a best concept, best idea is also welcome. And in case that you have something to share with us, you can contact with Meng Ze, the teacher assistant. You can find him by using the messenger in Facebook. Okay, is the information on the post. A special session on November 28th. It's an online presentation by the participants. Around 10 minutes plus, around 10 minutes to 50 minutes. So also here is a simple registration form in case that you are waiting to provide to provide a presentation or to share your study. You can register by using the form. Okay, so this is the lecture today, and see you all the next week. We still have another two talk.